Hey everybody, this video is going to go through F2 in the set theory unit. It is about conditional statements, converse, inverse, and contrapositive. So those are all different kinds of statements. We're going to take a look at what the different definitions are and how we can write these statements. The other thing that is in this lesson is something called a truth table, which we're also going to take a look at. Pretty much I don't think I've ever seen a provincial exam that doesn't have some question about these kinds of statements on it. So make sure that you follow along and we'll get started. So we're going to start with a logical argument. So when we're making an argument, there is some kind of premise and there is a conclusion to it. So what we are going to be doing is we are going to be making statements that have a hypothesis and a conclusion, and we're going to see what that looks like in each of these different kinds of statements. An argument is valid, so it's true, if the conclusion has been arrived at through accepted forms of reasoning. So what we're going to be looking at are conditional statements, and what a conditional statement is it has this format: if something, 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 then something, something, something happens, okay? So in each of these conditional statements, we're going to have if, our hypothesis, whatever that is, then our conclusion that results from it. Another way that we can think about it is if P happens, then Q happens. Okay, so this P and Q, those letters are going to be coming up quite a bit. So for example, if it is a Monday, then it is a school day. You could say the same thing. If it is a Wednesday or Thursday, then it is a school day. Converse is when we take a conditional statement and we flip our P and our Q. Okay, so our original conditional statement was if it is a Monday, then it is a school day. If we flip that around, if it is a school day, then it is a Monday. Now, sometimes our converse statements are going to be true. Sometimes they're not going to be true, so we have to kind of think about it logically. So for example, if it is a school day, then does that mean it's Monday? Well, no, not necessarily, because it could be a Tuesday or a Wednesday or a Thursday or a Friday. So this is when we introduce the idea of counterexamples, which is when we can disprove it by saying, well, no, that's not the case because so-and-so is true. So just like what I was saying, if it is a school day, it doesn't necessarily have to be Monday. It could be any other weekday. If a statement is biconditional, that means that the conditional statement and the converse are both true. And we say, this is kind of the notation here, P with the left and right arrow, Q. That means biconditional. That means P and Q is correct, like if P, then Q, and if Q, then P. The arrow kind of goes both ways. And we use these words here, if and only if. So P, if and only if Q. Again, we're going to take a look at some examples to see what that looks like. So our first example, if P, then Q. So we're going to say if a person cannot distinguish between certain colors, then that person is colorblind. If we flip the converse, so the first one is our conditional statement, then the converse is if a person is colorblind, then that person cannot distinguish between certain colors. So we just flipped our arguments around. So both of these statements are true, so we can write it as a biconditional statement and say a person cannot distinguish between certain colors if and only if that person is colorblind. Okay, so that if and only if is the important part in a biconditional statement. Now we can argue whether that's true or not. I mean, colorblindness shows up in a lot of different forms. You could be completely colorblind or just be color deficient in some way. But the point is, the general point I think is true if it follows the biconditional criteria. So here we have another example, and this is going to get more into the truth tables that I was talking about at the beginning. So we have a hypothesis that says it is raining outside, so that's my P. And my conclusion, we practice indoors. So what we're going to do is we are going to be writing 4 different statements here. We're going to check whether the statement is true or whether we can disprove it with a counterexample. So the first one, let's assume that the hypothesis and the conclusion are true. So I'm going to say P is true and Q is also true. So if they are both true, we would say if it is raining outside, then we practice indoors. And I think we can both agree that when it is raining outside, teams tend to not necessarily have practices outside. So we could say that this entire statement is true. Okay, so the statement is true. Okay, so we said P is true, Q is true. We wrote the statement if they are true, and we can conclude that the statement is true. Now, what happens if we say P is false, but we keep Q as being true? So now what this statement looks like would say, if it is not raining outside, okay, so now we're saying it's false. We change this to not, but our conclusion stays the same. Then we practice indoors. Okay, so in this case, say if it's not raining outside, so say it's sunny outside. We could say, if it is sunny outside, do we practice indoors? And I think the answer would be no. We tend to practice outdoors when it is not raining outside, when it is sunny outside. So in this case, this statement is false, and we can prove it using a counterexample. Okay, now let's consider the case where P is true and Q is false. So our statement will be, if it is raining outside, again, P is true, so we're not changing it. Then we could say we do not practice indoors, or we could say then we practice outdoors. So now we need to ask ourselves again, is this a true statement? Is it not a true statement? So in this case, if it is raining outside, do we tend to practice outside? I would say no. So this one is false. I'm going to go back to case number 2, and you could argue that this is a true statement, just because, like, even though it is not raining outside, you could still practice indoors technically. So I think I'm going to change this to true, because really it could be true either way. Now the last case that we're going to consider is if both of them are false. So P is false and Q is false. So what that means is, if it is not raining, so again we're negating it, we're flipping it to make it negative, then we practice outdoors. Okay, so again, we flip the Q to change it from indoors to outdoors. And again, if it's not raining, so say it is sunny outside, then we would tend to practice outdoors. So I would say that this statement is true. So from this, we can make a truth table. So we have our P and our Q, and then we're going to say, is our conclusion true or false? So the first one was true, and we said that the statement was true. The second one, we said P was false, and Q is true, well, we said that that was true. When we said P is true and Q is false, our conclusion was false. And when we said they are both false, we ended up with a conclusion that is true. So what can we see from the truth table? Well, it is only false when the hypothesis is true and the conclusion is false. All right, for any other combination, we ended up with a true statement, but that is the one that when we wrote it isn't true. Again, the other one is kind of iffy. You could kind of go both ways on it, but in this case, we're going to say that it is true. Now, these are a bunch of truth tables that have, this first one here, this is the one that we just did, P then Q. If we take the biconditional statements, it is only true if both of my conditions are the same. So true, true gives me true. False, false gives me true. Any mixed up combination gives me false. If we start negating something, so remember this symbol means P complement. It's like the opposite. It's things that are not P. It's just going to flip the arguments around. So true becomes false. False becomes true. Then we have these notations here that we talked about in set theory. So P and Q and then P or Q. So P and Q, the only time it's true, the conclusion, they both have to be true. If any one of them is false, it's going to end up being false. And for or, it is the opposite. As long as one of them are true, the answer is true. If they are both false, then the answer is false. So we're going to take a look at this example 3 here at the bottom of the page, and we're going to use these truth tables to fill in these the boxes here. So my hypothesis is a number is even, so that's going to be my P. The conclusion, the number is a multiple of 3, so that is my Q. Okay, so we have a set of numbers here. First one here is 21. So 21 for P, is 21 even? The answer is no, so this is false. Then for Q, is the number of multiple of 3? Yes, it is. So that is true. So only one of P or Q have to be true. So my conclusion is that is true. This is P or Q. If we do the same thing for 12, 12 is an even number. 12 is a multiple of 3. So that is true. 15 is not an even number, so that's false. 15 is a multiple of 3, so that's true. 7 is not an even number. 7 is not a multiple of 3. So because those are both false, my conclusion is false. And when we do the same thing, this one is for P and Q. So in this case, both of them have to be true for P and Q to be true. If one of them is false, then the entire thing is false. So we have the same statements here. False, true, 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 false, true, false, false. But now, because for 21 it is false, then the overall conclusion for both is going to be false. True, true is true. False, true is false. And false, false is false. All right, now we are going to get into inverse and contrapositive statements. So we talked about the conditional statement. We talked about the converse, where we flip it around. Now an inverse statement is when we negate both of the hypothesis and the conclusion of a conditional statement. So if my conditional statement is, if a number is even, then it is divisible by true. The inverse of that, if a number is not even, then it is not divisible by 2. Okay, and this statement might be a true statement, it might not be a true statement. So you have to kind of, again, think it through logically and come up with the conclusion on your own. The contrapositive is when we take the converse statement and then negate it. Okay, so we negate the hypothesis, and the conclusion, but we do that of the converse of the conditional statement. So again, if we take this conditional statement, if a number is even, then it is divisible by 2. The converse, we flip them around. If a number is divisible by 2, then it is even. The contrapositive is the negative converse. If a number is not divisible by 2, then it is not even. So we're going to take a look at this conditional statement here. We are going to take a look at the actual statement, the inverse, and the contrapositive. We are going to say whether it is true or not, and then we are going to, if it isn't true, we're going to prove it by giving a counterexample. So the statement is, if today is February 29th, then it is a leap year. This is a true statement because only leap years have February 29th as a date. If it's not a leap year, it does not have that as a date. So that is true. The inverse, so again, this is when we're going to negate it. So we're going to say, if today is not February 29th, then it is not a leap year. So is this true? Is this not true? Well, just because today is not February 29th, so assume it's February 28th. Can we assume that this is not a leap year? The answer is no, because tomorrow could or could not be February 29th. We don't actually know. We can't prove whether tomorrow is February 29th or not. Okay, so we can't necessarily prove that this is a true statement or not, so we're going to say that this is false. We can only say it's true, obviously if it's true, but if not, if we can provide a counterexample, then it is going to be false. The contrapositive is, if it is not a leap year, then today is not February 29th. Okay, so we just took our inverse statement and we flipped the arguments around. So if it is not a leap year, then today is not February 29th. And this is a true statement because February 29th can only happen in a leap year. So again, just kind of wrapping this up, there are often at least one question on the provincial exam that talks about conditional statements, inverse, converse, contrapositive. It's up to you to know how to write those statements, and it's up to you to verify whether they are true statements or not.